Frame relay basics. In the early 1980s, a technology was needed that could support high-volume bursty data while at the same time decreasing latency. In 1984, frame relay was developed to do exactly that. In this nugget, we're going to start with a look at the history that led up to the development of frame relay. Then we will define the key terms and devices used in a frame relay network. Once we've built this broad foundation on terminology, we will take a more granular look at the encapsulation types available on a Cisco router for frame relay. Next, we will discover the function of a data link circuit identifier, and then we're going to take a look at committed information rate and see how it is used in a frame relay network. And we're going to end up with a configuration example. The history of frame relay started with a need, and that need, as we mentioned in the intro, was a support of bursty data. So what we're going to do is start our history discussion with a discussion on time division multiplexing versus statistical time division multiplexing. Now this discussion could get very in-depth, and that would be beyond the scope of the CCNA. So simply understood, we're going to explain it this way. TDM is represented here. I have a four-way intersection. Each of these lanes has a stop sign associated with it. So if a vehicle comes up to this intersection, it has to stop. Regardless if traffic is passing through the intersection or not, it has to come to a complete stop, wait its turn, and then proceed to the intersection. That's the key there. It has to wait its turn. Depending on how many lanes you have associated with this intersection, that's how long you have to wait until your turn could come around, especially if the intersection is full. Now, when we're talking about statistical TDM, it's the same intersection, but it has a yield sign. So if a vehicle is coming up to this intersection and is able to see that there is no traffic coming in either direction, it is free to take the intersection as it pleases. In other words, let's say that these were computers on each end here, vying for a medium. This computer, if it could tell that nobody else was on the wire, then it could transmit as much data as it needs to, regardless of anybody else there having to wait its turn, as you would hear, even if nobody else was within the intersection. For this history section, we're going to build ourselves a timeline. So we're going to start that timeline with TDM support. As we just discussed, we needed support of bursty traffic. So as TDM was there, statistical TDM was developed so that we could do exactly that. If one device, one port, one computer had more traffic to send and the others didn't have any, then it could continually use that line. Once statistical TDM was developed, you had different protocols there. The first, or one of the first to be developed, was X.25. So frame relay was not the first STDM protocol to be developed, and X.25 did address a lot of the bursty support that they needed. But remember, there were two parts to the support. Support of bursty traffic, and at the same time, a low latency, decreasing latency. X.25 was founded in a time where the copper wasn't that reliable, and neither were the local area networks for that fact or the wide area. So what they had to do is build in a lot of error correction capabilities, and it adds a lot of overhead to that protocol or that technology. So this is where frame relay came into effect. In 1984, it was developed to make a faster packet switching network. So here we have frame relay. Now, it didn't catch on really quickly. In fact, it didn't catch on right off the bat because it wasn't standardized. There was no interoperability between the different vendors. So along in 1990, a frame relay consortium was developed or founded, and it was Cisco was one of the companies, Stratacom was another, Nortel was another, which is Northern Telecom, and then also you had DEC. These four companies came together, made a frame relay consortium, and said, we're going to take the basics of frame relay as they were developed in 1984, but we're going to add extensions. And these extensions are going to make, one, the frame relay interoperability go up because it'll standardize within at least these four companies, and at the same time, it's going to add global addressing and some other common or optional functions that can be added. Now, what you have to remember is that this frame relay consortium was not a standards body. In other words, it did not have responsibility internationally or even within the United States to develop standards. They simply came up with this idea, if you will. And later on, the bodies that did have responsibility for standardization in America, ANSI, which is the American National Standards Institute, and in the international body was ITU-T, which is the International Telecommunications Union. They came through and said, you know what? We agree with you. This is a good idea. We're going to make our own specifications, and they're going to be based on this 1990 development here where the extensions were added to frame relay. A good understanding of how frame relay works has to start with a solid understanding of the terminology and the devices used in a frame relay network. So here we have the terminology section. Up here I have a network diagram that we're going to fill in as we discuss the different devices or terminologies that are used within frame relay. We're going to start off with frame relay network. What exactly makes up a frame relay network? And the answer to that is a telecommunications network that is based on frame relay technology. Sounds simple enough, but we need to get it out there. So the frame relay network exists from this computer, N1 to N2, all the way through what would normally be termed the frame relay cloud here, and then these devices. So let's talk about each of these devices in turn. First, we're going to define what's known as data terminal equipment. Now, there's two types of data terminal equipment. So let me give you the loose definition of a DTE. This is how you're commonly going to see it written. And that's simply a place where a termination point of a frame relay either circuit or the true endpoint of a frame relay connection. So let's see how that plays out. We have what's known as end devices in here. And these are, as we just said, the true source and true destination in a frame relay network when you're passing data. So that would be these devices here, because they source the data from N1 to N2. These are the computers or workstations that are involved in the network. Then we have interface devices. The job of an interface device is to interface, as you might have guessed, an end device into the frame relay network. So that's what this device is going to do. The end device is here. The frame relay network exists here, and you normally see that drawn as a cloud. So this area is going to be interfaced by router number 1, and part of its job is encapsulation. We're going to talk about that in more detail later in this nugget, but for right now, just understand that as N1 sends out a frame, that frame has no hint or sign of being involved in a frame relay network. It's not until it gets to this point that it is encapsulated to go across that frame relay fabric. Remember that encapsulation is as simple as wrapping an original data unit in another data unit. All right, now let's talk about data communications equipment. Also, this is going to be commonly termed as the DCE. Here we have the DTE, here's the DCE. This DCE is carrier-owned equipment when we're talking about frame relay, and it's the switches. So here we're going to have switches within the carrier that are dedicated to frame relay. It is important to understand that in this cloud that represents the frame relay network, it can be made up of one switch or many switches. It really just depends on the type of network that you're connecting to. So when we're talking about that, frame relay networks can be private, which means that one enterprise operates and owns that network, or it can be public, so a much larger scale, and you would normally join a public frame relay network through a telephone carrier. All right, let's move on with our definitions. The next thing we have is an access line. An access line is defined as a connection between a DTE device, namely the type of DTE device we're talking about is an interface device, and the frame relay switch or DCE device. So this is an access line. And then we have trunk lines. And these are connections between frame relay switches. So these are the trunk lines here. The most important term in frame relay to understand is the virtual circuit and what it identifies. The virtual circuit is an idea of an end-to-end connection between interface devices. So in this case of our scenario, from R1 to R2, a virtual circuit is created across the frame relay fabric in the cloud into the interface devices. The virtual circuit is not physical. It is what is known as a logical connection. And we have a diagram here to help explain that. Let's say that this illustrates the wire or the cabling involved from R1 over to R2. Obviously, it goes through different types of interfaces as well with these devices. But the cable, as it structures across, has a logical division within it that is called a virtual circuit. So each of these divisions will be called virtual circuits. Now there's two types of virtual circuits involved in frame relay. The first is a switched virtual circuit. And what this means, it's pretty much just a temporary virtual circuit, or on demand, if you will. Whenever we have traffic that needs to travel across this connection from R1 to R2, a virtual circuit will be built on demand, and it will only be up as long as we are passing data. So there's no idle state here. As soon as the data is done passing through this switch virtual circuit, it's torn down. Now, the other side of that, the other type that we have, is called a permanent virtual circuit, or a PVC. The way you build this is it's built manually from R1 through this frame relay network over to R2. And that permanent build means that we are going to have an idle state. In other words, whether there's data on the line or there's not data on this virtual circuit, it's still going to be up, which is a very important characteristic because if you recall, part of the demand for frame relay was the fact that it needed to handle bursty traffic. Now, the switched VCs don't take that long to bring up, but obviously they do take longer than a permanent VC because it's already up. And whenever you're dealing with bursty traffic, you don't want the traffic to burst and then have to deal with the setup time on an SVC, come across, and then the teardown time. So I think that the permanent virtual circuits are better for most instances. Let me give you an analogy to help you remember the difference between the two types. First, we're going to start with the permanent virtual circuit. I have two mountains here and I need to cross. And what I will do is build a permanent structure, a bridge, across the two. Now, it doesn't matter whether people are going across this bridge at a particular time or not, that bridge will still be standing and ready for that to happen. That's the permanent virtual circuit. Now, with the switch virtual circuit, you're going to have to use your sci-fi mind for me for a little while. Movies like Star Wars and other sci-fi movies will have a tunnel and little landing pads throughout that tunnel. Now, if you envision hallways coming off of these landing pads, obviously, that can lead into this junction, if you will, or intersection, as soon as somebody steps on this platform, a bridge extends across to the other side so that you can walk across. As soon as that person is on the other side safely, that bridge goes back to where it was, and then there's nothing within the middle. This is similar to what an SVC operation will be. And then another one can be created here. Make your passage across, it'll go back into where it came from, and then another can go as well. And this is an SVC type warp. Before we leave the terminology section, I want to clear up one possible point of confusion. These are frame relay switches that operate here. Now, you're used to switches operating at the data link layer, which is layer 2 of the OSI model. But when you walk up to one of these, if you ever get to see one, they're actually going to be routers set up for frame relay switching. Now, you're used to routers operating at the network layer, or layer 3 of the OSI model. Don't get thrown off. Once you type in the command frame relay switching, then at that point, this router is going to operate at the layer 2 for frame relay interfaces. Encapsulation has been mentioned in our terminology discussion already, but now we're going to take a more detailed look of exactly what happens when we're talking about encapsulation on a frame relay network. Here we have our network depiction again, complete with our DTE devices, these being the interface devices, and then also our DCE devices, the frame relay switches that exist within the frame relay cloud. All right, now let's look at encapsulation. N1 is going to send out a data unit. And this data unit, as mentioned earlier, has nothing that tells you it's going to exist on a frame relay network. In fact, N1 isn't aware of that. It's not until it gets to router 1 that these changes take place. Here we're going to see representations of the OSI model, the different layers, this being the physical, the data link, and the network layer, so the first 3 layers, so that we can have a point of discussion. When this data unit comes into the router here, it is going to be decapsulated all the way up to layer 3. Then layer 3 is going to pass across within the router, and then we're going to encapsulate again. When we go for this encapsulation here, this is where the frame relay header is going to be placed around the data unit that used to exist as this original frame. So this frame exists right here, and now we have a new header, a new FCS, which is the frame check sequence, which means it's going to run a computation against the information that's in this protocol unit, and it's going to say, okay, I came up with a specific number, whatever it is. Let's say 1639. Now, when it arrives at the distant end, you need to do that same calculation and come up with the same number. If you don't, then this packet or data unit has been tampered with. All right, so we see here that this is where frame relay encapsulation actually takes place on the way down the protocol stack at the interface device. And it's going to exist all the way through. Here's a frame relay switch. It receives that new frame. It goes up to layer 2, transmits across, encapsulates again, sends over the wire, does the same thing at the next frame relay switch, across at layer 2, over the wire, until it gets to router number 2. It's going to decapsulate going up. In other words, it's going to strip the frame relay information here. And when this data unit is encapsulated again at this point, this is where it is going to exist as it did here when it took off from N1 and be transmitted into N2, which again will be unaware completely that this came through a frame relay network. What you see here is a generic representation of a frame relay frame. It is not exactly what is going to be used on a wire, but was simplified for the sake of our discussion. Now we're going to find out exactly the types of encapsulation that are available within the Cisco router for frame relay. And we're going to find that out when we use this command. At the configuration mode, once you're inside a specific serial interface, so this is config IF, you're going to type in the command encapsulation space frame relay, and at this point hit the question mark. And what you're going to get is two choices. One, simply return or hit enter, and the other is IETF, which is a standardization board that came up with a standard encapsulation that can be used between multiple vendors. In other words, Cisco and some other vendor, this is when you would use IETF. If it was simply Cisco to Cisco, then you could use the enter because that results in the default Cisco encapsulation. Now let me explain the difference between the two types of encapsulation, and you're going to see them here. The top is the Cisco encapsulation, and it is just like our generic representation in that it has flags, and it has the data, has the FCS, and a flag. This is the portion that is specific to Cisco. You're going to have an address field, and that is a 2-byte field, and you're also going to have a packet type field that's a 2-byte field that is used to identify the upper layer protocols that are being encapsulated by this frame. All right, now the other choice we had was IETF, and this is built on RFC 1490 as a standard. And again, we're going to have the flag, the data, the FCS, and the flag that we had in the generic representation. And then we're going to have the address field that is exactly the same as we see up here in the Cisco area. The rest of this specific fields for the IETF frame are going to be the control field, a pad if needed up to 1 byte. So 1 byte in the control field, 1 byte in the pad, and then what's known as a network layer protocol identifier. Simply put, it does the same function as this packet type, it just does it in a different way, and it does it in a way that can be standardized between multiple vendors, where this packet type is specific to Cisco. Let's demonstrate this in the router. All right, as you can see, I'm at the privilege mode. I'm going to type in configure from terminal, and at that point, as I had mentioned, I need to be in an interface. I'm in router 1, and I'm going to go into interface serial 0. Once you're in there, you can type in your encapsulation command, complete with shortcuts, so I don't have to type out the whole word encapsulation. And then I'm going to type in frame relay, frame dash relay, remember that or it won't let you complete your command, then the question mark. And here's where we have our choices. Again, the IETF, as we had mentioned, it uses RFC 1490, and then also it's been RFC 2427 has been revised as well. Or you can simply hit enter, and that's going to default for the Cisco type of encapsulation, and that's what we're going to do here. Now you're encapsulating the Cisco frame as we see flag, address, packet type, data, FCS, and flag. Now we're able to do that, like I mentioned earlier, between Cisco devices. So if I'm running from this device over to this device, it's no problem. But if I have a third vendor here, some other vendor that is not Cisco, and I need frame relay to exist here as well, I'd have to use the IETF form. Regardless of which type of encapsulation you use, the most important function of these frames is the addressing section here that is going to let you know what DELSI is associated with that particular frame. And the DELSI is the equivalent to the MAC address in most local area network connections. In other words, it's the layer 2 identifier that you're going to find for addressing. Now, what we're going to have is a DELSI that is significant or unique per physical channel, which means that virtual connection that you have here, a DELSI will not exist across that entire virtual connection. It's going to exist on the physical channel, which is from the switch within the frame relay network over to your router that interfaces with that switch. So your DTE to the DCE at the frame relay network, this channel, a DELSI exists here. So that means that another DELSI will exist between the switch and the other end that you're communicating with over here at R2. Another name for this physical channel is the access line, as we defined it in the frame relay terminology that interfaces the DTE to the DCE. All right, let's take a look at the frame specifically. This address portion, we're going to break out and show in more detail here. What we're going to have is 2 bytes, which is the equivalent of 16 bits, right? So we have to number those. We're going to have 1 through 6 here, 7 and 8 available at the end. And here we're going to have 1 through 4 in the second byte, then 5, 6, 7, and the 8-bit represented here. This is what we're going to have within those pieces or fields within the address. Specifications have been written for this data link connection identifier to be represented in different lengths, but the standard or default length is 10 bits long. And that's why we see within our address field here 6 bits for the high order bits of the DELSI, in other words, the first 6, and then 4 bits after that to complete the rest of the DELSI. These are called the low order bits of the DELSI. The rest of these fields will be defined in the Advanced Concepts Frame Relay Nugget. They are the CR. These have to do with error notification. This is the discard eligibility, and these are the extensions, EA. And again, those will be explained in more detail in a later nugget. All right, for now, let's continue to define the DELSI. Another thing about the DELSI you need to know is its range. You can range between 16 and 1007 when you're talking about local significant DELSI. So let me explain what I mean by local significance. Within a frame relay network, whatever I assign as a DELSI to identify this pipe or this virtual circuit is going to be unique only in the fact between this router and this switch. It doesn't matter what happens between this router and this switch. There is a division here. So that really means that I could have a DELSI here of 16 and a DELSI of 16 on this end as well. This poses no problem for the frame relay network because remember, DELSI has significance from the DTE over to the DCE. But in most cases, even when we're dealing with locally significant DELSIs, they will be different on each end. So let's say that this here will be a DELSI of 26 while the other is 16. This idea of locally significant layer 2 addressing is probably the biggest hurdle to get over in frame relay networks, especially if you're coming from a LAN environment where layer 2 addresses have to be unique on the individual devices. So let me give you an analogy to help carry you through this. Let's say we have a target here. Transmitting data down a frame relay network interface off of a router is much like target practice with a gun. All right, I'm going to draw my gun here, no laughing. At the end of the gun, I have a sight here, and it's used for aiming at my end target. And then I fire into the target. Now this illustrates the IP address at the distant end. In other words, the IP address that exists here, if I'm transmitting out of router 1 across this frame relay network to this distant end. Now the site is going to represent my DELSI. Understand that that DELSI resides locally. In other words, it's on my gun, on my interface, and it's used just so that I can aim straight down that virtual connection that exists from end to end. Let's take a trip back into the router so that we can complete the second of the 2 mandatory commands to make basic frame relay work. Remember that the first one was we find a serial interface and we set its encapsulation type to frame relay. Now what we need to do is set up the DELSI on that interface. So here we go. I'm going to get into conft interface serial 0, and at this point I'm going to type in the command frame-relay interface. Now there's no abbreviation of interface because there's a second part to this little line, DELSI. And now I can pick anywhere in my range, let me hit the question mark, between 16 and 1007, just like I showed you on the whiteboard. In this case, we're going to opt for 201. You hit enter, Control Z, show the running config, and what we're going to see is both commands that we need for frame relay setup. Let me hit advance here, and there they are. DELSI is 201, encapsulation is frame relay, and they all exist on the serial interface. We started this nugget by looking at the history that led to the development of frame relay. Then we looked at terminology and devices that are involved in a frame relay network. Encapsulation was covered after that, and we just went over the DELSI. Now we're going to look at the committed information rate. The committed information rate, again, exists between the access line from the router, which is a DTE, over to the switch, which serves as our DCE. So in this respect, it shares the same boundaries as our DELSI. All right, now what is the committed information rate? It's the guaranteed minimum bandwidth at any given time that will be supported between these 2 points. Let me give you an analogy to try to help explain this. Let's say that I have a neighborhood here with 3 homes. And that neighborhood is serviced by a central office or a dial central office from the telephone company for its telephone connection. So each one has cabling to the home, and they can support one phone call at a time on their one telephone cable. We will define these three units as one community of interest as we are, one common group. Now, the CO, or the central office, has the ability to support 3 phone calls from that common group. But the way we're used to things happening, in fact, the way it does happen today, is that home number 1, if it has a phone call to make, it takes up its line. Even if home number 2 and home number 3 aren't using their phone lines, home number 1 does not have the ability to make more than one call at a time. So let me show you what the world would be like, or the telephone network, if it resembled a frame relay network. What it would do at that point is it would say, okay, each of you homes, I guarantee you one phone line at any given time. This is your committed information rate. But I have technology available that says if home number 1 gets on the phone line and it takes up its one phone line and it has to make another call, simply somebody gets on another phone and dials out, and now I have 2 simultaneous calls coming from home number 1 because 2 and 3 aren't using their phone lines. And then let's say a third person wants to get on the phone and make a call as well. Simply pick up the phone and make your call. I have 3 conversations coming from home number 1. Its committed information rate was 1 call, but it's able to burst up to 3. Now let's say at a given time, home number 2 picks up the phone because it wants to make a call. As soon as it picks up the phone, it gets its one dedicated line, and this second line, that is disconnected, that conversation. And now it gets its committed information rate, home number 2 does, of 1 phone call, but home number 1 still has an extra one because 3 isn't using his. Wouldn't that be a wonderful world if frame relay technology was developed into the phone network, and let's just say our community? Now let's apply that technology into our network that we developed earlier, remembering that this is our frame relay cloud complete with switches in the backbone. Routers will exist in communities of interest. In other words, this will be R3 and R4. All 3 of these routers can have connections into this common switch. And what that switch says is, I have a big fat pipe into the frame relay network. You can use more than your committed information rate, in other words, more than you're actually paying for, as long as the other parties in your communities of interest aren't using theirs. And you can burst for a specific period of time up to the point that they need their committed information rate. Now, one of the coolest aspects of this whole thing is that you don't even know your neighbors. Where here you would in our analogy. These are separate companies. R1 is a connection into your company. These other companies that you are able to burst into their bandwidth, you have no idea who they are, and you don't really even care. In the last section of this nugget, I'm going to give you a configuration example of basic frame relay. Let me familiarize you with our diagram here. We're going to have 2 routers involved, router number 1 and router number 2, obviously going through a frame relay switch. Now what we want to encapsulate is IP traffic, so I had to assign IP addresses. 192.168.2.1 exists here on router 1. 192.168.2.2 exists here on router 2. This is further evidence that even though this seems like a layer 3 device, in other words, it can be a router, it's operating at layer 2 because there's no IP addresses assigned within the interfaces on this router. All right, and the other thing I had to set up, obviously, is encapsulation frame relay. I hit enter here so that we use the default, which is Cisco, which is fine because I'm between 2 Cisco devices. And then frame relay interface DELSI. I have to assign DELSIs. I'm going to assign 201 here at router number 1, and then DELSI 202 at router number 2. Keep in mind that as we've gone through this nugget, in router number 1, we've already entered these commands as we went over them individually. Let me show you that. Here within router number 1, we're going to show configuration, and the first thing we're going to get is the first 2 Ethernets. So let's go into serial 0 configuration. And that's where we see that we did indeed set up encapsulation frame relay, as we see up here, and then the frame relay interface DELSI is already set to 201, which is exactly what we said we needed within our diagram. Now we're going to go into router 2 and do the exact same thing. I'm in the privilege mode here. Let me get into configuration. And the difference here is we're going to use a different interface. It's going to be interface serial 1, but we're still going to go forward with exactly the same commands we used for frame relay setup in the other router. So encap, short for encapsulation, frame dash relay, enter there, and we're opting for the Cisco relay encapsulation, and then we set up frame dash relay interface that cannot be abbreviated, dash Delcy, and then we're going to opt for Delcy 202 here at this router. All right, let's close that down, and then we're done with our configuration on router number 2. Next, we have to verify our connectivity, make sure we set everything up okay. And the way we're going to do that is with our old friend, the ping command. We've set up IP addresses, so we're going to ping from router 1 over to IP address 192.168.2.2, and that's how we're going to verify connectivity. So let's do that up here. Get outside of the show conf that we had running there, and then ping 192.168.2.2, hit enter, and there you go. We have connectivity. Let's do the same thing with router number 2. Bring it up so that we can see our diagram. Ping the opposite end, 192.168.2.1, and we have connectivity there as well. A myriad of show commands also exist that can be used whenever we're troubleshooting frame relay networks, so we don't have to rely on the ping command to verify connectivity across, but that's going to be covered in a later nugget, troubleshooting frame relay. We started this nugget with a look at the history that led up to the development of frame relay and the fact that XTRAT25, although that technology could handle bursty traffic, because of the advanced error recovery, it wasn't fast enough. We needed less latency. Then we looked at the terminology and the devices involved in a frame relay network, followed by the 2 types of encapsulation that we can opt for with a Cisco router, and that was the Cisco proprietary encapsulation and also the IETF encapsulation. Then we saw the function and form of the Delcy, the data link connection identifier, as it's used within frame relay. We discussed committed information rate and the fact that if the telephone network operated the same way, it'd be a much better world. And then we ended up with a configuration example that showed you router 1 and router 2 both configured for frame relay, and the fact that we could verify connectivity across that network with the ping command. I hope this has been informative for you, and I'd like to thank you for viewing.